Hello, we are starting topic 4 on logic circuit minimization. Okay, we'll go back to some of the little circuits we did before and see how we turned some idea into some gates, and then we refer back to them and say, well, these methods that we use weren't really any regular methods. They weren't something that I could scale up into larger circuits, and then we justify the fact that we need some more formulated ways of designing circuits or minimizing circuits. So let's start with logic circuit realization. Okay, first we go into ad hoc methods, and then we say, well, ad hoc methods really aren't that good. Then we say, okay, let's do something like Boolean algebra. Then we go into examples. Then we go into the next step, which is Carnot map, which is a really graphical representation of Boolean algebra. And then we talk about timings and things. Okay, so let's start with this. And for now, logic circuit realization. Look at this circuit. This is the overflow detector circuit that we have already done, and you know how it works and everything. And what we did is we kind of the problem was small, right? So we said that, okay, let's say the output is 1 when the input is 1, the output sign bit is 0, or the output sign bit is 1, and then the two input sign bits are 0, and this gives us the overflow circuit for the adder. So if here is an adder that is adding two 8-bit numbers, we take the two sign bits of the I'm just doing what we have done before, just to give you a reminder of what has happened. See, this is the sum input. This is the two inputs here going into the this is A7, this is B7, this is S7, and then we are calling these capital A for one of the bits, capital B for one of the bits, and capital S for that. And then we are doing this overflow circuit, and that gives me the V output. And so for overflow, we don't really care about the other bits of the adder, A0, A0 through A7. So that's an overflow circuit. It works, and we can build it. And what if I want to make some changes to it? What if I want to make it an all NAND circuit? So what do? I use some techniques like this. We know that NAND is an AND gate with an inverter. Okay, or the other way around, actually. An AND gate is an AND with an inverter. Okay, this is an AND gate. But then I look at this circuit, I say, well, I have AND gates. I don't like AND gates because AND gates are not realizable directly by transistors and by CMOS logic, by CMOS transistors. So I really need NAND. So what do? I say, well, let's do this. Let's take this AND gate and replace it with an AND with an inverter. And so I'm able to still realize that same circuit I showed you a few minutes ago, which is this thing over here. But then this time I'm using an ANDs here. And how about the output? Well, the output, the same thing. The output here, I have an OR gate and OR is what? Is a NOR, like that, and an inverter in front of it. Okay, so I'm using ad hoc methods. I'm using things I know from little gates and all that to change this circuit to NAND gate. What if I want to make some more changes? Let's say I want to make all the circuit, change it to all NAND. Well, in that case, remember that we can bubble the outputs. We can outputs of AND, inputs of NOR, and then put bubbles, and then outputs of AND bubbled, inputs of OR bubbled, and therefore I have this is an AND gate, this is an AND gate, and the other one is also an AND gate. So again, I'm using some ad hoc methods for making such changes. Okay. So there are many alternatives that depending on my application, the application being the timing, the number of transistors, the delay of the circuit, even power consumption and all that, I can make changes in this circuit, or maybe for the look of the circuit. Okay. For example, this is another exact representation of the circuit that you see over here. Okay. A, B, S bar, A bar, B bar, S. Okay, see, this is the same circuit as this one, but this one looks better because I can read it better because the bubbles cancel out, and then I just say, well, these three inputs here are being, these three inputs here are being ANDed. Instead of saying ANDed, I say ANDed, these three are ANDed, and then the result are ORed together. So in a way, in my mind, I cancel out the bubbles that are on the two lines of the on the two ends of the line, and read the first gate as an AND gate and this one as an OR gate. But again, this is an AND realization. Only the way I read it is this. What I'm really saying is there are many ways I can represent a circuit. Okay. Maybe in my library, I only have two input AND gates and OR gates. And I want to change this original circuit to two input gates. All right, that's the fourth alternative. And so I know that a gate like an AND gate, a 4-input AND gate or a 3-input AND gate, can be broken into this. Okay. Or it can be broken into this. Okay. But here I have a 3-input AND gate, and therefore it can be broken into something like this. Okay. Again, I'm using ad hoc methods, and then these ad hoc methods, I'm very limited in what I do with these ad hoc methods. Well, yeah, I did change this circuit into 2-input AND gates. Or 2-input gates, because the output gate is a 2-input OR gate anyway. And so why are we saying all this? We are saying all this because depending on the application, you have a circuit, and depending on the application, and I haven't said everything yet, okay? There are situations where because of the timing, because of some hazard that happens on the output, because of all of these, you want to change the circuit diagram. You want to change things in the circuit. And for this small circuit that we are dealing with, this overflow circuit, yeah, we can play with it, even though we haven't explored all the possibilities. But then for the small circuits, maybe we can do that. But when the circuit gets larger, then how do I do these manipulations? Okay? So what we are really saying is this. There are a million ways, not exactly a million, but there are many ways that you can change a circuit into various formats. And the question is, do I have enough tools? Do I have any formulation for doing this? And how can I count on, let's say I want to minimize a large circle. How can I be sure that this circle is really minimized? How can I be sure that these ad hoc methods I'm using turn the circuit into the correct circuit? Maybe they make, maybe these ad hoc methods I use, I make a mistake. So how do I verify that? So there are a lot of topics, a lot of things that go wrong when you are doing ad hoc. Okay? Not only that, you are limited to for small circuits only. So this is what we do. We say, well, let's use Boolean algebra. Okay? What is Boolean algebra? Boolean algebra is a formulation, is an algebra that only uses 1 and 0. It is based on switches. Okay, let's do this. We have talked about transistors. Transistors are on-off switches. But see, before transistors, there were relays. Okay, a relay is an on-off switch as well. A relay has a port that either connects or disconnects two ports together, exactly like an NMOS transistor. Okay? And our logic is based on this. Once again, before transistor existed, computers were built using relays. So what we are really using from transistor is the on-off property of it. And you can buy these little relays in electronic shops. The on-off behavior, we are using 0, 1, which we have talked about in the binary systems. Then we say this: if I have two switches in series, in a way I'm doing ANDing. Look at this. I have two switches here. Let me run the animation again. Two switches here, A and B, they are in series. And then if I have a positive voltage over here, the two switches being in series turn the light on. Okay, so in the back of my mind, I said, well, anytime I have two switches in series, I am ANDing them together. Anytime I have three switches in series, I'm ANDing them together. If I have two switches in parallel, I'm ORing them together. Okay? ORing them together means that the light goes on either by A being turned on, or the switch conducting, or B conducting. Either one is okay. And therefore, this is switching logic. And we use these series transistors, or series switches, let's say, to call this ANDing, call this ORing. And then the other operation that I have is NOT, or complement. NOT means if I'm complementing a switch, means that the complemented switch turns on or conducts if, for example, A bar, or the complement of A, conducts if A does not conduct if A conducts. Okay, so I have these three operations, and that's all there is to it. How about our variables? The variables are either 0 or 1. Forget about the Z and the X that I talked about in regard to transistors. They don't exist in Boolean algebra. Okay? So, I have an algebra that I can do ANDing, and ANDing implies two switches in series. I can do ORing, two switches in parallel. I can do complementing, and my variables, every variable in Boolean algebra has two values, either 0 or 1. Based on this, we form an algebra for manipulation of these gates, these switches. Then we come up with a set of rules. And all the rules, again, they use ANDing, ORing, nothing, and also the variables are 0 or 1. These are the operators. Let's start with Boolean algebra rules. Okay? First rule. It says if you not something twice, if you complement something twice, is as if you haven't complemented it, obviously. Okay? If I tell you complement this switch again, complement it, well, you say, well, I'm not going to complement it at all because it's the same thing. This is called double negation. Next rule. Next rule says if you have a switch, now, whenever you see an OR, okay, let me go back here also. I said not is represented by a bar, and is represented by a dot, or is represented by plus. These are the three operators, okay? And also, and not has higher precedence than and has higher precedence than or. So if I say A and B or C, A is complemented first. Okay, so complementing happens first. Let me draw it down here. A bar B or C. Complementing happens first, and then ANDing happens. Okay, and then ORing happens. That means the precedence is with the not, and then the and then the or. All right, so let's go back. Second rule says A or 1. A or 1 means what? A or 1 means if I have a switch, let's go back to the switch again, and the switch is A, and then the other switch is 1, that means it's conducting all the time. Well, what it means is, well, whether this is conducting or not, it doesn't matter. Whether A is on or off doesn't matter. I always have to switch on. And therefore, A or 1 is always 1. How about A and 0? Let's think about the switch again. A and 0 means that I have a switch A, the other switch is always not conducting. So what happens is A goes on and off, there is no path to the light bulb, and therefore the result A ended with 0 is 0. So initially, when you are thinking about these logics, think about these switches, then you get used to forming the you get used to understanding these logics. A and 1 is A. Okay, let's think about it. A and 1 is A. 1 means the switch is always conducting, and therefore it means like it is a piece of wire, and therefore A and 1 just becomes A. A or 0, then it looks like the 0 here is always open, and therefore again A or 0 is A. A and A, that means two switches work exactly like each other and they are in series, and therefore that becomes A. A or A, two switches in parallel, they go on, they go off, they go on, they go off together, and therefore this is again A. Okay? What if I have A or A or A or A? Well, that's also A. These are the rules. These are the set of rules that we learn, that we will play with, that we will be using for minimization and for manipulation of logic circuits. A and A bar, okay? A and A bar, two switches that work in opposite direction, okay? What happens is, in either case, one of them is off, and therefore A and A bar is 0. How about A or A bar? Two switches that are in parallel and they work in opposite directions, but then in either case you have a conduction path, and therefore A or A bar is 1. Okay? A or B is the same as B or A. Okay, two switches. You put them one on top, one on the bottom, or reverse them. Doesn't make any difference. And therefore, A or B is B or A. Again, a lot of these rules, by just thinking about the switches, you can understand how they are working. A and B is the same as B and A. Again, the same reason for that. A Now we are going into associative laws. We are going into rules that are a little bit more complex. And from this point on, I don't show you switches because you can always think about switches, even for very complex ones. But at this point, I'm saying A and B and C is the same as A and B and C. This is called associative. The next one, the second associative, says if you are doing A or B or C, doesn't matter whether you do B or C, or you do A or B, or you do A or C, and then or with B. Okay? And so that's another rule here. Let's look at the other one, distributive law. Distributive is the first one, looks very similar to the way we use regular algebra, right? A multiplied by B plus C is AB plus AC. Okay, but in Boolean algebra, not only you have this, which is this first distributive law, you can also distribute over the or, meaning that A or B and C is A or B ANDed with A or C. Okay, that's called distributive law. And we can prove all of these by let's say by tables, by looking at the values 0 and 1. Let me do the second distributive. I have A, B, C. Since I have 3 values, they can only take 8 different combinations. Okay. And then I have, let's form B ANDed with C. Okay. B ANDed with C is 0 here, because B and C are 0, is 0 here, is 0 here, is a 1 here, is 0 here, 0 here, 0 here, 1 here. Okay, let's form A or B and C. That means A or B and C, that means the left hand side. Let's form this. Okay, and so what I'm doing is ORing the B and C column with A. So this is a 0, this is a 0, this is a 0, this is a 1. Okay, let me show it to you here. See here, what I'm doing is I'm taking this and this, forming this. Okay, and the previous one, I was taking this, forming this. Okay. And so let's go back to taking the yellows and putting it there. This is a 1 here, this is a 1 here, this is a 1 here, this is a 1 here. Okay. Now that we are done with the left hand side, let's do the right hand side, or this one here. Okay, I hope I have enough room. I'm gonna do A or B. A or B, I put it in this column. Okay, A or B, I'm gonna put it in this column. A or B is 0 here, is 0 here, is a 1 here, is a 1 here, is a 1 here, is a 1 here, 1, 1. Okay, let's do A or C, A or C. Okay, A or C, a 0 here, a 1 here, a 0 here, a 1 here, a 1 here, and then a 1 here, a 1 here, a 1 here. And then what do I do for the right hand side? Okay, for the right hand side, which is A or B, ended with A or C. This is the right hand side. And then this is the this one is the left hand side. Okay, let's do the right hand side now. The right hand side is ending of the last two columns, a 0 here, a 0 here, a 0 here, a 1 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 here. What do we see? We see that the right hand side, the this column over here, let me use a dark blue here, this column is no different than, let's say, this column, and therefore we have proved the second distributive law. You can do the same exact thing for all of these rules, Boolean rules. All right, the next one is absorption, meaning that A or with A and B is no different than A. What it means is really A and B absorbs in A. And then again, you can use this table to prove this. The second absorption law is, it says A and A or B is A, and that is, again, it means that the A or B gets absorbed in the A, reducing it just to a simple A. You can either use this table here, or you can play with the switches the way I showed there to prove that the right hand side and the left hand side are the same. Then we have what is called the De Morgan's law, and then De Morgan's law says this. It says if you have an expression E1 ended with expression E2 and you complement the whole thing, what you do is you break the complementer here, and then where you break the complementer, you change the operation. What it means is this was and, so it becomes or. What it means is E1 ended with E2 is the same as E1 bar ORed with E2 bar. And then it also works the opposite. That means if you have the A or B with the bar, you break the bar, and then that becomes A bar, B bar. Now the bars here are a little bit small, but this is supposed to be like this. All right, that's called De Morgan's law. And the last rule that we have is called duality. Duality says this. It says, take an expression. Take an expression which is good. Whatever expression. Okay, here. A or with B and C or with E bar, for example. Okay? And let's say this is something. The dual of this is when you change all the ands to ors, all the ors to ands, all the zeros to ones, all the ones to zeros. So if you have an expression, the dual of it is changing ands to ors to ands, zeros to one, one to zeros. Okay? It says if one of these expressions is good, the dual of it is also good. Okay, so let's go back up. Let's say you have proven this, you are sure of this. Change the or to and, the 1 to 0, the 1 to 0. The second expression is the dual of the first one. So if the first one is good, so is the second one. That applies to everything. And also that applies to the distributive law that we had a little bit problem understanding, right? See, because we are all used to this first distributive law. We all know this. That's easy for us. But now let's take this and come up with the dual of it. The and changes to or. The or changes to and on both sides. The and changes to or. The or changes to and. The and changes to or. And therefore, this is distributive law. The second distributive law, the first one is true, so is the second. All right, we have talked about the rules, and now let's do some examples. I start with my simple example of the overflow circuit.